before we jump in, I wanted to ask, does anyone know what this is a picture of? Earth, yes. Yeah, this is a picture from Earth taken by the Voyager 1 space probe in 1990 from 8 billion kilometers away. And I like to start with this picture because it helps put our place in the universe in perspective. You know, that's us, that little pixel, that little mote of dust suspended in the sunbeam, as astronomer Carl Sagan puts it. So let's start by talking about the environmental impacts that our energy use has on that mote of dust suspended in the sunbeam. So in the first class, Diana talked about how there's often a difference between the private cost that we pay to consume a good or service and the total cost to society. And the difference between that private cost and the total cost to society is externality. They can be positive externalities or negative externalities. But often in the case of energy, we're looking at negative externalities like pollution, like instability in the Middle East, et cetera. So it's hard to manage externalities of natural resources in particular because they're what are called common goods. And common goods have two key characteristics. First, that they're rivalrous, and second, that they're non-excludable. So rivalrous means that that use of the resource diminishes its availability to somebody else. So if you and I are hypothetically neighboring farmers, and we have a pond, and I take water from that pond, that resource becomes less available to you. So that resource is rivalrous. So in addition, common goods are non-excludable, which means that it's hard to prevent somebody from using it or regulating it. For example, you can't keep somebody from breathing the air. Okay, so you can imagine the carbon budget is also a common good. Yeah, you guys touch on a lot of the good ones. All right, so natural resources like these that are common goods, they're subject to an economic phenomenon called the tragedy of the commons, whereby individuals acting in their own self-interest and rationally according to their own self-interest will ultimately deplete a shared common good, even if it's contrary to the interests of society as a whole. So the implications of the tragedy of the commons is significant. It means that we need to actively manage and regulate our natural resources if we don't want to deplete them entirely. So I'm going to show a few charts that get at how we as a society have been using our natural resources. And there's lots of good stuff in these charts. You know, I think as you have probably gathered, we like to show a lot of charts on our slides in this class. But bear with me because these are great to understand. So these charts over here, they show that since the 1950s, we've seen a significant global acceleration of population growth, of economic growth measured as GDP or gross domestic product, and urbanization. And with it, we've seen a significant acceleration in the demand for goods and services like energy, fertilizer, fresh water, and paper. And as a result, we've seen significant increases in levels of pollution and the depletion of our natural resources, like forests and fisheries, and also our carbon budget. So in the chart on the left, the socioeconomic trends that we see are broken out by gradations of orange and yellow. And the darker orange at the bottom is what are called OECD countries, which is a term that's used largely to describe developed countries. So most of the population growth that we see in the upper left-hand corner since the 1950s has come from the developing world, the non-OECD countries, in particular the BRICS, Brazil, Russia, India, China, and South Africa. But the vast majority of GDP growth has come from the developed world. So one of the challenges, the sustainable development challenges that we're facing today in this world is, how do we manage our natural resource use as the developing world, where we've seen a lot of population growth, continues to demand the same goods and services of the developed world. And so how do we do that sustainably without entirely depleting our natural resources and falling prey to the tragedy of the commons? Okay, so I showed this graph to you in the climate change class, but this is why we talk so much about energy about the environment in an energy class, because our energy use is a huge contributor to a wide range of environmental impacts. And we'll dive more into each of these today. So I mentioned this at the beginning, but one of the big takeaways that I hope you get from this class today is that the impact of these environmental impacts has been disproportionately borne by underserved communities and continues to be. And this is one of the reasons why we've seen the emergence of the environmental justice movement in the US. Black communities and other people of color, including tribes in the US, they bear a disproportionate burden of the environmental and climate impacts of our activities, including our energy use. And it's because of this that in the 1980s, we saw the emergence of the environmental justice movement in the US. This is a photo from Warren County, North Carolina, which is one of the few counties in the state that has a majority Black population. And in this photo, they came together in 1982 to protest the siting of a toxic waste dump in their backyard. It was really a key historical event highlighting the environmental racism in this country and the environmental justice movement. So there are lots of ways that environmental and climate inequities related to energy exist internationally. We talked about global inequities and their impact on coming to a global agreement on climate change earlier during the climate lecture. But today I'm going to talk about how systemic racism exists in the US, in our own backyard. So in the US, many studies have shown that the racial profile of your residential community is the single biggest factor determining whether you live near a hazardous waste facility, like a coal-fired power plant or an oil refinery or a toxic waste dump. Almost every city in the US has some form of racial segregation. This map on the right-hand side, it depicts racial segregation in the US by the warmer colors in the map. And you can see, even though it doesn't look like there's a lot outside of the Southeast, if you zoom in, you can see that every single city has some form of racial segregation. And this racial segregation has specific origins. They date back to intentionally prejudicial federal housing and zoning policies of the 1940s and 50s that were able to quite successfully divide neighborhoods along Black and white lines. And this process was known as redlining. These patterns of segregation have proven really hard to reverse, and they've been detrimental to Black communities in many ways. Black communities, they often experience disparate lack of investment in public infrastructure. They have less of a voice in local government and zoning laws. And it's common to see these Black communities zoned for industrial operations. So we'll talk more about what this means in the context of energy, but at a high level, the pollution associated with our energy use, whether you're talking about our vehicles or our fossil fuel power plants, they're worst right next to the source of pollution. So we'll see pictures later of how these red-lined Black communities are often located right next to highways, which is a huge source of our air pollution. Okay, so let's jump back to talking about environmental impacts. And one high-level point that I want to make is that environmental impacts occur throughout the life cycle of our energy use, from manufacturing, extraction on the upstream side, to transportation and refining and the midstream, as well as electric power plant combustion, to distribution and end use. So everything we do has an environmental impact. There's no free lunch. For example, even in the case of renewable energy, you've got wind turbines that can have impacts on birds and bats. You've got solar PV modules that take energy to manufacture. So everything has an environmental impact, and we have to actively understand those and manage them, regardless of if you're talking about renewable energy or fossil fuels. The other point that I want to make here is that when you're approaching an issue, it's really important to think about the whole system and not just silo in on one aspect of the system. Let's give an example. For example, if you're thinking about your energy use or your water use and how you might reduce your water usage, you might think that maybe you can take shorter showers, you can not ask for water at restaurants. But if you took a step back and looked at overall water usage in the US, you would realize that your own domestic water use is only a small portion of overall usage. I'll show you this breakdown and in a little bit and how energy plays a role. But by and large, agriculture in the US is the biggest consumption source of water. Similarly, if you're thinking about your own greenhouse gas emissions, it's important to think about how you can reduce your own GHGs, but it's also important to recognize that it's only one part of the puzzle. If you can see that homes make up a small sliver of US greenhouse gas emissions, and if you take a step back and look at US greenhouse gas emissions in the context of global emissions, which is the blue sliver there, it's still only a portion of the picture. So if we only focus on what we can have a direct impact on, and we lose sight of the broader picture, we rob ourselves of the opportunity to think creatively about how to have a bigger impact and really move the needle. And I love what Sandra was talking about, walking the walk, getting her own hybrid vehicle, but also thinking about the bigger ways that she could have an impact through things like voting and how she engages in her community and also her career, right? She's having an impact by helping tribal nations develop clean energy projects, which is pretty cool. All right, so let's talk about the environmental impacts of energy use in these 4 impact categories. And let's start with air, which is one of the big ones. Okay, so I'm going to crowdsource this one. So how does air pollution form from our energy use? Let's think about this. So what are fossil fuels made up with primarily? Chemically. Hydrocarbons, yes. Okay, and what happens when we combust them? Yeah, combines with oxygen, and we get CO2. What else might happen in this process? What else what other air pollutants might get generated? Incomplete combustion, yes. And what might that result in? Yeah, you can get. What else? Sulfur dioxide, yes, yeah. If there's sulfur in your fossil fuels, you might get sulfur dioxide. And if the flame burns hot enough, then the fuels might combine with nitrogen in the air, and you'll get nitrogen dioxide or nitrogen oxides. Okay, so there could be mercury in what else might be in your fossil fuels? Lead. Okay. Okay, and there are some secondary air pollutants that form from some of these pollutants. Another air pollutant that can form from incomplete combustion is volatile organic compounds. Volatile organic compounds are anything that can easily change from a liquid or a solid to a gas. So when you go to a gas station and you smell gasoline, you're smelling VOCs. VOCs could be harmful and carcinogenic, depending on the source, or they could be, naturally occurring in nature. Like, if you're standing around pine trees, you smell pine. That's a VOC. So VOCs, they can come from direct emission, like methane leaks. Methane is a VOC, or they could come from evaporation of your fuel or incomplete combustion. So the secondary air pollutants that form from these guys, if you've got VOCs that combine with NOx and sunlight, that's how you get O3, ozone. And then if ozone combines, the one that we forgot, sorry guys, is particulate matter. So particulate matter can also come from incomplete combustion of your fuels, or if your fuels have other things in them, like dirt. So if ozone combines with particulate matter, that's how you get smog. All right, so that's air pollution. This just summarizes what we talked about. Basically, if you burn, evaporate, or emit a hydrocarbon, you get air pollutants. And we talked about how, in the climate change lecture, that our energy use is the primary contributor to greenhouse gases in the US and worldwide. And so is the primary contributor to most of the warming that we've seen today. Different energy resources have different levels of greenhouse gas emissions. This chart, it shows the result of a study of the life cycle greenhouse gas emissions of different electricity generation resources based on surveys of hundreds of peer-reviewed studies. And it's life cycle, so it includes upstream and downstream and midstream, looking at the system. So you can see that a lot of the renewable energy resources perform fairly well in terms of the median, which is the dark diamond, particularly relative to fossil fuel resources. I will call out, hydropower has a really broad range. This is because of a couple different reasons. First, most hydropower electric generation plants weren't built just for electricity generation. They were built for things like irrigation and flood management. And the project slapped on a power plant just as a side benefit. So there's an attribution question here of whether or not these emissions should be attributed to the electricity generation. And taking a step back, the reason why hydropower has emissions is because that constant flooding of vegetation can release methane. The other reason why there's such a broad range here is because some hydropower could be like a big dam, but other hydropower, a smaller relative portion of our electricity mix comes from run-of-river hydropower, where you don't actually have a reservoir where you have that flooding of the vegetation. You also see significant range from, for biomass, and that's because the GHG emissions from biomass largely depend on the feedstock. If it comes from corn, for example, corn requires a lot of energy and fertilizer inputs, and that's why you see that significant potential for greenhouse gas emissions there. Ultimately, though, by and large, fossil fuels make up the primary source of greenhouse gas emissions in the energy sector. So because we talked about climate change in its own lecture a couple weeks ago, that's the extent of how I'm going to talk about greenhouse gas emissions in today's class. For the rest of the class, I want to focus on other air pollutants like particulate matter, lead and mercury, and whatnot. Again, this is showing you that our energy usage is the primary source of most of these pollutants. So these air pollutants have a variety of different impacts on health and the environment. I want to call out a couple of them. Particulate matter is considered the most deadly, and PM, particulate matter, is categorized based on size. You've got the larger PM, PM10, and the smaller PM, PM2.5. So PM2.5 means that the particulate matter is smaller than 2.5 micrometers. And 1 micron is about 1/50th the size of a strand of hair. So PM2.5 is pretty much invisible. It's known as the invisible killer. And it's one of the biggest health risks because it can get into people's systems. It can get into your lungs, it can get into your hearts and your organs and cause organ damage and respiratory illness. All right, I also want to call out lead and mercury. They're both what are called bioaccumulative, which means that organisms have a limited ability to process these pollutants. And because of this, top predators like tuna can often have significant accumulations of lead and mercury in their system because of the animals that they're eating. This is one of the reasons why pregnant women are told that they shouldn't consume tuna, because it can have a really big negative impact on the growing babies. So in the US, we have been fairly successful at regulating all of these pollutants, except for perhaps CO2, since the passage of the Clean Air Act and subsequent amendments beginning in the 1970s. All right, so air pollutants, as I've talked about, they have significant impacts on human lives, ones that often go undiscounted because it's not something that we can see, and there's often a lag. There's if somebody gets diagnosed with lung cancer or has asthma, we don't necessarily directly attribute it to the air we breathe. But countless studies have made that, scientific studies have made that connection. About 1 in 5 deaths worldwide are linked to air pollution. In the US, air pollution is considered the number 3 cause of death, with about 200,000 deaths annually. So this is significant. Deaths from air pollution are even worse in the developing world. A little over half of the global deaths from air pollution are attributed to ambient or outdoor air pollution, and the rest are from indoor air pollution. And this is because still about 1/3 of the world relies on dirty cooking fuels. Something that I imagine you guys are going to be talking more about in the Energy for the Developing World lecture. Okay, so you saw from this map that air pollution varies by country, but even within the US, as we talked about, the impacts of air pollution are also vary geographically and by population. Countless studies have shown that Black and Hispanic populations in the US are disproportionately exposed to air pollution. With a 2017 Harvard study finding that Black Americans are 3 times more likely to die from exposure to air pollution than other groups. So this is significant. And this is because of the historical racial segregation and the redlining that we talked about, where Black communities and communities of color are more likely to be located next to those sources of pollution. This is an example of a predominantly Black community in Orlando, Florida, basically surrounded by freeways. And this is, pretty common. If you look at the predominantly Black communities in Las Vegas, for example, a region where I'm focused on, many of them are located along Highway I-15 as well. And these are considered by the US Census persistent poverty communities that really need a lot of help. Okay, so let's transition from talking about air to talking about water. There are really 3 main categories of water impacts. You've got water withdrawals, water consumption, and contamination. Water withdrawals refers to withdrawing water from a source that you ultimately put back into the same source. And the most common water withdrawal is thermoelectric power plant cooling, where a power plant uses the steam cycle that Diana talked about, I think, in the first class, to take water from a source like a lake or an ocean, uses it for cooling, and then puts it right back into the same source. Albeit a little bit warmer, maybe there was some evaporation on the way, which would be considered consumption, but most of the water was put back, and that's considered a withdrawal. With consumption, unlike withdrawals, you don't return the water to the original source. An example could be, a farmer using water to water their crops. And then you've got water contamination, where pollutants, including like lead and mercury and SOx, sulfur dioxide in the air, ultimately settles into the water and can contaminate it. Or you've got, toxic byproducts like coal ash from coal-fired power plants that could also have a history of contaminating water. So within our energy systems, water is consumed for many different processes throughout the energy fuel life cycle. You've got the upstream water usage for things like drilling, mining, hydraulic fracturing. You've got midstream, which is primarily for thermoelectric power plant cooling, and then the downstream for things like waste management, like coal ash handling. All right, so this chart, it shows you withdrawals of water overall within the US and what the different sources are. And you can see that thermoelectric power plant cooling is the #1 source of withdrawals in the US. It makes up 41%. Irrigation comes right after it at 37%. But if you looked at this chart in terms of consumption, because thermoelectric cooling largely returns the water to the original source, thermoelectric cooling would reduce to about 10% of our water consumption. So pretty significant. The other thing to note here is that this chart from the USGS, it includes saltwater consumption, and about 1/5 of thermoelectric cooling in the US is from the ocean. I want to make a quick note about the energy-water nexus. Not only does energy use require water, but water resources and water consumption require energy as well. An estimated 13% of energy consumption in the US is used to move, heat, and treat water. This is a picture of the Edmonston pumping station that is used to pump water from Northern California down to Southern California over the Tehachapi Pass. If you did get the chance to visit CAISO, the California ISO, it's the grid operator in California, they'll talk about how this is the biggest point source of electricity demand in California. Let's look at freshwater consumption by each energy resource use in the US, which is shown on the right-hand side here. You've got total consumption of different energy resources and the percent of total freshwater consumed. These charts are from a study that were actually developed by a former lecturer and TA of this class, Emily Grubert, who's now at the University of Notre Dame. But you can immediately, well, not immediately, because really it's good to normalize the right-hand chart based on how much energy you're producing, right? Rather than looking at those in an absolute manner. But if you did normalize it, then the biggest consumer of fresh water in the US is hydropower. And that's really because of the evaporation of water in the reservoir. Another significant poor performer is ethanol, which is water used for growing corn. So corn-based ethanol makes up about 10% of the gasoline that comes out of the pump today. And about 30% of US corn is used for alcohol for ethanol. And corn is one of the biggest crops that we grow here in the US. So the water and other inputs like fertilizer are significant resource usage for corn ethanol production. The best performers in terms of freshwater consumed are wind and solar PV, followed by, and this surprises a lot of people, but oil and natural gas as well. Okay, so let's talk about land requirements. We talked about air, we talked about water, let's talk about land. And there are really 4 main categories of energy-related land use to think about. There's land that's needed for upstream extraction of fuel, like there's none needed for hydro, for wind or solar, because the resource is naturally occurring in our environment. But there's quite a bit that's needed for coal mining, for uranium mining and milling, less, but still a significant amount needed for things like natural gas drilling and extraction. There's also land needed for transportation of the fuel or electricity, like pipelines or electricity transmission. There's land needed for the power plant itself. In the case of hydro, that would be a significant amount of land, right? Because you've got the reservoir there, although there's still that attribution question. And then there's land that's needed for managing energy waste streams, things like coal ash, nuclear waste, et cetera. If anyone's ever visited a coal-fired power plant, one of the first things that you'll likely see is the big coal ash pits. So this table, it compares land use of various electricity resources, breaking it down by the land required for the lifetime fuel production, so that's upstream fuel production and downstream fuel waste management, as well as what's needed for the power plant area. I purposely actually didn't put this data in a chart because the numbers can be deceiving. Like we talked about with hydro, that's really a dual use resource where the primary purpose for a lot of the hydroelectric power plants that we have, those hydro dams, is irrigation and flood control. And also not a primary reason, but we all like to go boating sometimes, so recreation as well. Same with wind. The power plant area that's needed on a gross basis is pretty significant, but really only 2% of that land is used for the actual turbines and the ancillary equipment itself. And typically when you see a wind farm, it's also being used for things like crop production or grazing. Solar too can also, if it's sited on rooftops, you're not using land. But one of the things that we hear a lot with solar projects and solar power plants is that, they use so much land, which, it's true that the power plant itself uses a significant amount of land, but again, you don't have that upstream fuel production. So if you look at it on a life cycle basis compared to things like coal and nuclear and natural gas, they actually become a lot more comparable. All right, so the final environmental impact category I want to talk about is wildlife. And I want to talk about a framework for thinking about wildlife impacts and give you the example of bird deaths. You probably hear a lot in the media, or maybe from our former president, that wind turbines kill a lot of birds. It's important to put that in context and ask questions like, how well does current regulation manage those bird impacts? Should we be worried about regulating other behaviors that or activities that have a more significant impact on birds than wind turbines? As you can see in this table on the right, cats are actually the biggest killers of birds. Unfortunately, I have a house cat, and I'm not going to give her up because of this table. Thank you for making that point. So that was my next question. What type of birds are we talking about? So my cat is not going to kill a bald eagle. It's more likely to be the other way around, as much as I think that she's fierce. So that's one of the big challenges of wind turbines, right, is that they can kill endangered birds, like bald eagles, and others. But another big question is, what's the alternative? If the alternative is continuing to source electricity from fossil fuels, like coal-fired power plants, then climate change is estimated to have a far greater impact on birds and bird species, including those endangered ones, those bigger ones, than wind turbines. So hopefully this helps you think about how complex some of these challenges can be, but the importance of thinking about the bigger system. All right, so I hope a takeaway for you from this lecture is that, by and large, the highest growth clean energy resources like wind, solar, and electric vehicles are much better than fossil fuels, or are much better than their fossil fuel counterparts in terms of environmental impacts. So the clean energy transition that we're seeing today is going to be a boon for the environment. However, there's no free lunch. Everything we do has an environmental impact. So clean energy has environmental impacts that have to be managed. Chief among them are the fact that clean energy resources are more minerals intensive to build than their fossil fuel counterparts. Something that we'll talk about more in this lecture, but this chart just gives you a sense of how much minerals goes into an electric car versus a conventional car. And minerals extraction, that's a mining process, right? But we'll talk about some of the ways that we can mitigate that in the energy storage lecture, for example, through things like recycling. All right. Thank you all.